I guess I only need one of these. In this unit, we're going to talk about rational functions and what those look like. And for the first section, we're not going to do much graphing at all. It's going to be focused more on the details of the graphs, what different moving parts there are. Tomorrow we'll put it kind of all together and actually see some pictures of these and how to graph them. The only two graphs that you're going to have to worry about, one of them you've already seen, y equals 1 over x. That's one of the parent functions that we learned as part of our unit a few months ago. So you got to remember this graph, which has vertical and horizontal asymptotes at x equals 0 and at y equals 0. A lot of times in math, like if the x and y axis are asymptotes, we never really put dotted lines on them because we have a reference for us to graph. But as soon as these things start getting shifted, it's very important that you have those on your graph. Now, the other graph that you have yet to really focus on too much is this one. It's very similar to this 1 over x graph, but the only difference is that all our x values are squared. And you guys know that if you square a negative number, what happens? It becomes positive. So this part of the graph that is normally underneath is now going to get kind of flipped up so that it's positive. Okay, kind of the same shape. You still have 1, 1 and negative 1, 1 as part of the graph. Okay, but it gets a little flatter, a little quicker as we go towards 0. This one kind of gets there a little slower. This one gets there a little quicker. But as far as the shapes are concerned, all you have to remember is that we're above the horizontal asymptote. So here we still have x equals 0 and y equals 0 as vertical and horizontal asymptotes. Okay? Now, what we're going to be focusing on today is first finding the domain of a rational function, finding vertical asymptotes of a rational function. This is just kind of the multiplicity we'll talk about. That's not too much of the focus, but we'll talk about it. And then the fifth one, which is horizontal or oblique asymptotes. That's what we're going to talk about today. Okay? So then, first let's start with domain. A rational function has a numerator and a denominator. To find the domain, we've actually done these problems before. You take the denominator, and since you can never divide it by 0, you set it equal to 0. Okay? And then you figure out what values those are going to be. Now's not the time. I'm in the middle of notes here. So now, I lost my train of thought now. Where was I? Ah, yes. So once you figure out what values those are, that's going to help us figure out the domain. Okay, so we'll do that in a minute here. Vertical asymptotes. A function in lowest terms is the key. So you got to factor and cancel first if possible. Once you've done that step, in other words, once you've reduced the fraction, then you're going to go ahead and find the zeros of the denominator. Okay, so that's what you kind of need to put together right now, is that vertical asymptotes are from the zeros of the denominator. Okay? Now, yes? What? Well, we just did zeros last unit, right? How do you find the zero of something?
Where you look at the equation, you divide P's and Q's.
Well, you could use P's and Q's, but we're not going to have anything that's not hard. What's that? You just ask me. Here, let's look at a problem. What would the 0 for this denominator be?
Oh,
You see how you all know that?
wow.
Okay.
I think it's just
Does
the
it-
wording that tricks me.
Does that answer your question there?
Yeah.
Okay.
Wow.
And that translates to a vertical asymptote at that value. Okay. As far as what's happening near those vertical asymptotes, okay, this is something again that it's not the emphasis because we're going to have calculators anyway for the graphs, but it's kind of nice to know what you're getting into. The multiplicity of any 0 of the denominator tells us what kind of behavior there is. Okay, if it's odd multiplicity, here's an example. What's the 0 of this denominator? Oh boy. 0. 0 is the denominator, right? What's the multiplicity of that 0? 1, because it's to the first power. Do you see how one end we're going up towards infinity, and for the other one we're going down towards negative infinity?
Yeah.
That always happens with odd multiplicities. So your only options here, let's say there's an asymptote at x equals a. If one side of it we get close to infinity, on the other side we must be getting close to negative infinity, or going the opposite direction. These could be flipped. Maybe you get close to infinity on the left, and then on the right we get down to negative infinity. But that's the key, is on one side we're going down, on the other we're going up. Here we're going up and then down. So anytime you see odd multiplicity, that's what you can expect. What's the multiplicity for this denominator? 2. What's the difference? Well, now both of these are going which way? To positive infinity. Or the other option is these could be flipped underneath, and now they would both go to negative infinity. Does that make sense? So anything with even multiplicity, let's say here we have another asymptote at x equals a. Either they're both headed up towards infinity on either side, or if things are flipped around, yeah, they're both going down towards negative infinity on either side. Okay. Any questions on that so far? Yes. 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 Okay. So the last kind of asymptotes that we're going to talk about is all related to the degree of each part of it. Okay? You guys remember what degree means, right?
Yeah.
Some of you are shaking your head no, some of you are saying yes. What's the degree of this numerator right here?
2.
What's this degree?
1.
Everybody remembers that, right? Okay. There are a few different scenarios that come from this. If the degree of the numerator is greater than the degree of the denominator, we have something called an oblique asymptote. And in order to find the oblique asymptote, you simply divide and find the quotient. We've actually done that. Remember the synthetic division with the P's and Q's that we did? I mean, we're not going to do P's and Q's anymore, but we would still do synthetic division potentially to figure out the asymptote. Okay? That's if the degree of the numerator is bigger than the degree of the denominator. So actually this one that we were looking at, this would be an example of when there would be an oblique asymptote, potentially. Degree 2, degree 1. Okay? The second option is that the degrees are exactly equal to each other. So if the degree of the numerator and the degree of the denominator are equal, then we have leading coefficient divided by leading coefficient. And I'll kind of illustrate that with an example and explain why that works.
Wait, what's an oblique asymptote?
We don't know yet.
Wow.
So, yes, here we have a horizontal asymptote, and since the degrees are both 2, we just take the leading coefficients and divide them. So, Brandon, you were right. leading coefficient over leading coefficient is just 2 over 5. Okay? Now, it's not just a magic trick or it's not a formula. It actually kind of makes sense. So if you think about this, if you make x really, really big or really, really negative, same thing. Imagine like 10, for example. 10 squared is what? 100 times 2. If you add 3, still pretty close to 200, right? Not really going to go up that much. Here, if I multiply or do 10 squared and multiply it by 5, what do I get? 500 plus a little bit, close to 500, right? What's 200 divided by 500? It's basically 2 over 5. Does that make sense? As these numbers get larger and larger, we get closer and closer to 2/5. And these, the 3 and the 2x and 1 start meaning less and less. Okay? If we look at a table, you can kind of see what I'm talking about a little better. So if you type this into the graphing calculator, 2x squared plus 3 divided by the denominator, 5x squared plus 2x plus 1. Whoop, that's not what I wanted. Okay, you can start scrolling. Do you see how these are pretty much not going anywhere?
Yeah.
They're pretty, I mean, they're changing, but very, very little. Let's fast forward. It's pretty much, it's not the same. I mean, you guys see these are changing over here, right? But what is this really, what decimal is this really close to? 0.4, which is 2 over 5. Okay? That is also 40%, yeah. Very good. Okay. Second, or last scenario, sorry. We did if the degree is larger in the numerator. We did if the degrees are the same. And now here we're doing if the degree of the numerator is less than the degree of the denominator. So something like x to the second plus 3x divided by, what kind of degrees would I have to have down here? Third, what else? Anything bigger, yeah. So anything bigger than 2. Let's do x to the third plus 5. Okay? Whenever you see this, that the degree of the numerator is smaller than the degree of the denominator, here the horizontal asymptote is always y equals 0. Okay, and it's the same argument as we had up here. If you make x really large, like 10 or 100 or 1,000, when you do 10 squared, you get 100. Add 3, pretty much still 100, right? 10 cubed is now 1,000. Add 5, still pretty close to 1,000, right? But when you divide those numbers, what's 100 divided by 1,000? 1 over 10, which is really close to 0. And as we can do that here as well. Let's type this one. X squared plus 3x divided by x to the third plus 5. So as we get really large, you can see these values start to go down, right?
Yes.
But all of a sudden, they're going to start to slow down. And now, even if we jump forward, go down to like 500 again. You sure? 1,000? You guys know this means 9.8 times 10 to the minus 4, right? Yeah. So it's just it's basically these values, but now the 1 is shifted over and it's 0.0001, etc. Okay, so still getting smaller, getting close to 0, but that's That's where that comes from, okay? So before we do any of these, here's what you need to know. How to find domain, which we've already done, so that shouldn't take too long. How to find a vertical asymptote, and then how to figure out whether there is an oblique asymptote or a horizontal asymptote and what those are going to be. As far as putting this all together and graphing this, we'll do that tomorrow, okay? And it'll be not so bad. I mean, you guys will have a calculator available to help you sketch these, but you need to be able to find the details out on your own, like the ones that we're talking about today, okay? Let's look at example 1. When I have a fraction, how do I find the domain? That's something else that we would do. Yeah. What can we not have in the denominator?
0.
Because you can never divide by 0, right? So, if we say that x plus 5 can never be 0, then what value of x can we never have? Negative 5. And there's the domain. Okay? Now, whether you write it this way or in interval notation, I really don't have a preference unless you're asked for a specific format. Okay? I don't know, on Math Excel they might ask for either, but just be ready for either one. Okay? Here, if we found the domain, we would say x squared minus 4 cannot equal 0. And then you have a couple of options. You can either add 4 and then square root both sides, so then x could not be plus or minus 2. You could also factor using difference of squares to get x minus 2, x plus 2, and also get the same domain value. Okay? Any questions on domain? Okay. This is the only graphing that you're going to do in this section. It's nothing related to all this complicated stuff we just kind of learned. It's more, can you take this graph and shift it left, right, and reflect, and things that we've done long time ago, right? And we're also going to add to that mix now this new function, 1 over x squared. That's it, though. So, for example, this one, what's the parent graph?
X.
1 over x, yes. What about here?
X squared.
Good. The only thing now is that we're shifted a little bit. Do you guys remember how to work with your transformations? What does this do? Left 1, down 2. Very good. Whoops, I wrote dow 2. Down 2.
How's it now doing?
Down 2. You guys are... Okay. What does this one do?
Right 2 up 1.
Right 2 up 1.
Why do you retweet all the time?
Okay. So if you want to be successful at graphing these without making this more difficult than it needs to be, here's the easiest way to do it. What point, so let's start with the 1 over x graph. What point is kind of like the center of everything that's happening? 0, 0, I would say. I mean, it's not part of the graph. You guys understand it's not part of the graph, right?
Yeah.
But it's kind of a good reference point because the horizontal and vertical asymptotes cross through at 0, 0. And then everything's symmetrical with that point. Does that make sense? Okay?
Yes, sir.
So, with something like this, when you move left 1 and down 2, I would start with that 0, 0 point because that's a good reference point to start with, and do left 1, down 2. And so this is where all the asymptotes intersect. So I'm going to go ahead and draw in the vertical and the horizontal asymptote, which are now, this is at y equals negative 2, and this one's at x equals 1 instead of x equals 0. And if you know what the parent graph looks like,
-1 or 1?
oh, thank you. Thank you for catching that. Okay. So if this is your new origin or your new 0, 0, what point was this right here?
1.
1, 1, and then this one is So you can go right and up one and left and down one to get the graph. Does that make sense?
Yeah.
Right and up one, left and down one. And then you just fill in the shape of the graph. You don't need any other points besides those.
Yes.
Okay? Does that make sense, you guys?
Yeah, I love that.
Okay? Same thing with this graph. If I move right 2 and up 1, now this point right here is kind of the center, well, not the center, but the intersection of the asymptotes. So we have a vertical asymptote at x equals 2, a horizontal asymptote at y equals 1. And now, if you don't know, until you get really comfortable with it, what points are on the graph here? 1, 1, and negative 1, 1. So, go right 1 and up 1. Yeah, just copy the graph. Left 1 and up 1, and you're done.
One and done. Amen.
Okay? Any questions on that? How do you know if what's odd or even? Are you talking about like how it looks this way? It's because the parent graph is 1 over x squared. Anytime it's x squared, we know it's got to be like that. Anything else? Okay, last page. So here we're looking for vertical asymptotes. Okay? Before you find vertical asymptotes, you want to always reduce the fraction first. Okay? So don't just look at it and say, here's my vertical asymptotes. Let's go ahead and factor. So yeah, we're going to have to remember how to factor in this unit. Okay? How does x squared minus 9 factor?
Plus or minus 3i. Oh, bro, I did this wrong. I said equals 0.
Still wouldn't get plus or minus 3i.
Oh, no.
You were thinking it was plus 9.
Yeah.
Okay. How do you factor the denominator?
3 and 2.
2 and 3. And these both have to be negative. What do you notice? Can we reduce this at all? Yeah, you can cancel out this common factor right here. X minus 3 cancels. And so the only thing that we have to really figure out then is what the vertical asymptote is for this new, simpler, smaller function. How do I find the vertical asymptotes?
So they're even degrees. So
You're thinking horizontal. Hold that thought. Vertical. Vertical asymptotes come from where?
The denominator.
From what of the denominator? There we go. The zeros of the denominator. What's the 0 of this denominator?
2.
X equals 2. That's your vertical asymptote. Okay. Questions on that? Okay. This one.
oh, that was easy.
Can we factor the denominator? To what?
2x minus 3. 2x plus 3.
And so if you set each one of these equal to 0, you would add 3 divided by 2 or subtract 3 divided by 2. We get plus or minus 3 over 2 for the vertical asymptotes. So this one's got 2 of them. Okay? Any questions on the vertical asymptotes of a graph? Or how to find them? Okay. Willie, I think this is what you were talking about.
Yeah, a little bit.
Find the horizontal or oblique asymptotes. I'm going to leave the oblique asymptote examples for the end. Looking at this part A and part B, which one of these is going to have an oblique asymptote?
The first one.
Are you sure? Why B?
Because the numerator is greater.
The degree of the numerator is bigger, right? So this one's got an oblique. What about down here? The second one again. Okay. So these other examples right here are going to have horizontal asymptotes. Okay. So Willie, how would I find the horizontal asymptote for A?
A.
What do you know about the degrees here?
They're equal.
Yes, the degrees are the same.
The coefficient of the numerator over the leading coefficient.
Very good. So what would that give us?
That would be 3 over 2.
3 over 2. Good. Make sense so far? Okay. The next one with the horizontal asymptote is this one. Here we have a degree that's different. The degree of the numerator is smaller, right? So what does that translate to? Yeah, it's just y equals 0. It's always 0 if the degree in the denominator is the larger one.
I like those.
Mm-hmm. Okay. I'm going to modify this example here. Change this to a -1, x minus 1 down here in the denominator. Okay, sorry about that. But I think for our purposes, this will work better. Okay. So we haven't really talked about oblique asymptotes yet, but in the notes we did mention how to find them. Where is it? Page 2. So if you need to go back and you forget, it's this first case here. All you have to do, if there's an oblique asymptote, is actually divide and find the quotient, which we know how to do already from last unit, right? How would I divide this and find the quotient? 1 divided by into what coefficients?
3.
So it's just synthetic division. Okay. Bring down the 3. 3 times 1. Positive 2. Oh, okay, so you were talking about the remainder. Okay. What part of this is the quotient, though?
32.
So here's my quotient. This is the remainder. For oblique asymptotes, we don't pay attention to the remainder because it won't really affect the graph as it gets really large or really small. Okay, all we care about is this quotient.
3x
This is going to be 3x
plus 2.
plus 2. Okay.
That's it?
For now, yeah, that's it.
For now.
I mean, we're eventually going to graph these, you guys. Right now, we're just getting good at finding these details. Okay? And yeah, the graphing won't be too bad. All right, this one. I'm going to preface this by saying that you're probably not going to have anything to graph like this on an exam, and you'll see why in a second. To find the oblique asymptote, what number do I... Okay, and the coefficients are...
2, -1, 0.
Yeah, don't forget the placeholder.
Oh.
Bring down the 2. Multiply. Add. Multiply, you get 6. Add, you get 6. Multiply again. 15 is the remainder. Here is the quotient. What does this translate to? 2x squared plus 3x plus 6. That's kind of weird. Because look at everything else that we've seen.
Oh.
We have vertical, horizontal asymptotes, right? Vertical, horizontal, vertical, horizontal. Here we have an oblique, but that's just a line, right? If we actually graph this, you'd have an oblique asymptote that looks something like this, y equals 3x plus 2. This is a rough sketch, and I'm just doing this by hand. And then asymptote is going to be at 1. Okay, and if you graph it, I think what's most likely going to happen is that you're going to get something that looks like this. Okay, we'll talk more about how to get this tomorrow. Okay, but this is a whole nother ball game. I mean, this is a parabolic asymptote, which means then that this graph over here, instead of approaching this line, it approaches this parabola, which is very strange. It happens, but it's not something we're going to ask you guys to actually graph. Okay, but you should be aware of that. All right. Any questions?